Okay, it looks like we're live and the audio is working, so let's get right to it. I am at cryptozombies.io and I am learning how all about crypto. I did lesson 1 already and we are 50% through lesson 2. And so what's going to be amazing, I already love this. It's fantastic. To catch you up, a smart contract is literally, they use the word contract instead of class to define a class. That's it. Also, there's an emit event that communicates with web3.js, and it's very slick and well coupled. There's some global variables like someone's like Bitcoin identifier, whatever your crypto wallet thing, public key or whatever is. And what else? I'm sure there's something else that I'm forgetting, but we'll see it when we get to the code. And this is just going to be a walkthrough, and we're going to pick up where I left off. And the question is, this thing is kind of like not great. But let's see if I need to increase the size so I think we need to bump it up to like I think 200% is that's pretty. I think that's okay. Okay, that's great. Managing the feed over here. If you occasionally see me glance in that direction, that's what's going on over there. And let's see. Okay, so I'm just gonna read through this and then we're gonna edit it. In part 1, we made Zombie Factory. So we have a pragma specifying what version of the compiler we're using. We make a class. We label an event. We define some variables. It's a typed language, by the way, in case you didn't pick that up. We make a struct of zombies. We make an array of that struct. You can do maps, which I guess it's like to do dictionary, like you make to do dictionaries. The key is the address and it gives you a number. You give it a number, it gives you the address. In terms of function scoping within a class, you put it all the way here at the end. And even cooler, there's view and there's pure. I kind of blank out on what they are, but I'm sure we'll get them again. And then the return type is here. Let's see what else. This emits the event we defined up here, and that talks to our front end. This is user login stuff. Message.sender is who's coming to the thing, to your contract, so to speak. And it's a global variable, so you get to use it. And this is essentially saying you can create a random zombie if this person hasn't already created one. The require is kind of like an assert statement. What else? I think public operations go to the blockchain. And private one, I think do we have any examples here? This variable memory is just a local variable. And I guess that's really local variables are only in memory. Public or non-local global variables get written to the blockchain. So you'll see here that we have memory declaration types. They like to use the convention of underscore for private variables. Let's see. Other interesting stuff. View. I remember it just said the compiler complains about this, so we'll learn it quick enough. So anyway, that was the code we wrote before following lesson 1, and now that we're all caught up, let's go to middle of lesson 2 already. So there's inheritance, there's includes. It is very similar to how Java works. Very strong Java vibes, but a little bit less annoying syntax. It's like Pythonistic Java, and Java and just that it's typed and object-oriented. Anyway, let's get to chapter 7, storage versus memory, data location. Oh, okay. Well, let's see what they say, because like they kind of talked about this already. Storage and memory block. Here we go. Here, I'm just gonna read it. In Solidity, there are two locations you can store variables: in storage and in memory. Storage refers to variables stored permanently on the blockchain. Memory variables are temporary and are erased between external function calls to your contract. Think of it like your computer's hard disk versus RAM. I think that kind of lines up with what I said before. Cool. Most of the time, you don't need to use these keywords because Solidity handles them by default. State variables, variables declared outside of the functions, are by default storage and written permanently to the blockchain, while variables declared inside functions are memory and will disappear when the function call ends. Noted. Let's scroll up a little. However, there are times when you need to use these keywords, there are times when you do need to use these keywords, namely when dealing with structs and arrays. I did not post that I'm streaming. Yeah, whatever. Anyway, let's read this code. We make a contract called Sandwich Factory with a struct sandwich, and it has a name and a status, and we make an array of sandwich structs. Then we define this function, which is public, called eatSandwich. Okay. Does it cut off? Okay. I think, can I move this over at all? No? Okay, so we'll just scroll. Anyway, you can do declare an instance of the sandwich class with sandwiches of index. And I guess that's kind of like, they've used this pattern of when you're making a new object, you pass in the key, the unique key. Okay, seems pretty straightforward, but Solidity will give you, I'm just going to shrink this so I don't have to scroll. Yeah. All right, that's not too bad. I'll raise it back up when we need to type. Anyway, seems pretty straightforward, but Solidity will give you a warning telling you that you should explicitly declare storage or memory here. So instead, you should declare it with the storage keyword like this: sandwich storage type my sandwich. Sandwiches, in which case my sandwich is a pointer to sandwiches of underscore index. And in storage and my sandwich.status eaten, this will permanently chain sandwiches of index on the blockchain. Got it. Updates permanent. Yeah. If you just want to copy, you can use memory. This is just a very elaborate way to explain, local versus global variables. Right? This will just modify the temporary variable. So yeah, you're saying local or global. And have no effect on sandwiches, but you can do it this way if you want to. We'll just modify the temporary variable and have no effect on sandwiches of index +1. Okay, but you can do this: sandwiches of index +1 equals another sandwich. If you want to copy the changes back into the blockchain storage, because sandwiches is storage type. No, yeah, it's up here. I think you get it. Anyway, let's go zoom back in so you guys can read along and continue to scroll. Don't worry if you don't fully understand when to use which one yet. Throughout this tutorial, we'll tell you when to use storage and when to use memory. And the Solidity compiler will also give you warnings to let you know when you should be using one of these keywords. For now, it's enough to understand that there are cases where you'll need to explicitly declare storage or memory. Put it to the test. It's time to give our zombies the ability to feed and multiply. When a zombie feeds on some other life form, its DNA will combine with another life form's DNA to create a new zombie. Create a function called feed and multiply. It will take two parameters, underscore zombie ID, an unsigned integer, and underscore target DNA, also an unsigned integer. This function should be public. Okay, so start here. And they really mean it. This is a very fragile code checker. So anyway, we need to make a function called feed and multiply. And we'll take 2 parameters. Okay. uint underscore zombie ID and a target DNA. It'll also be an unsigned integer. And this is a public function blammo. All right. We don't want to let someone else feed our zombie. Makes sense. So first, let's make sure we own the zombie. Add a require statement. I talked about that before, remember? Add a require statement to verify that message.sender is equal to this zombie's owner, similar to how we did in createRandomZombie function. Okay. Let's go back to, yeah. That's our hint, createRandomZombie function. Okay. So make sure that the message.sender is, oh, this is a good one. Okay. So add a requirement statement to verify that message.sender is equal to the zombie's owner. Well, we have a zombie ID. All right. Oh, yeah, you need semicolons in this language, but what is zombie ID? New zombie ID, and is our zombie ID just zombie ID? We'll find out. Okay. We're going to need to get this zombie's DNA. Yes. So the next thing our function should do is declare a local zombie named myZombie. Okay, I'm not sure if this is right, but we'll find out soon enough. We're going to need to get this zombie's DNA, so the next thing our function should do is declare a local zombie. And like we learned from earlier in this thing, we'll make it a memory. Local, okay, yeah. My zombie. What am I thinking here? Which will be a storage, pointer. Got ahead of myself, I guess. I am using that right? Yeah. Zombie, zombie ID. Okay. Set this variable to be equal to index zombie ID in our zombies array. Zombie. Okay. Do I have a zombies array? What is going on here? Yeah, zombies. Okay. You should have 4 lines of code so far. 1, 2, 3, 4. Including the line with the closing curly brace. All right, check our answer. I knew it was wrong. Require. Let's look at this again. Like we did in the create. All right. That is also a problem. Let's see, semicolon needed, of course. Wow, I made a lot of typos here. This is what happens when you stream late at night after a long day. It didn't like that. Let's look at one of our previous function definitions. Blah, blah, blah. That's an event. Ah. String memory. Ah, okay. So I think this needs to be uint memory. And this needs to be uint memory. Right? Is that what we saw? Memory. Public. Private. Let's run this again. I did not like that memory. Okay. All right, let's look at the answer this time. We're kind of just warming up to this tonight. Oh, I have a zombie to owner function that I should be using. All right, well, let's type in what they have. Okay, so they did not use these memory things that we saw in our other file. Uint, all right, feed in multiply, uint, all right, zombie ID, all right, public, require zombie to owner. Am I missing that? Create zombie, generate random, create random zombie. Oh, zombie to owner is a dictionary. So I guess this, all right. So mapping is, all right. So like in terms of, this is, all right, actually, yeah. Look, you get events, you get just low level data types, you get a struct, you get arrays, you have mappings. This is like a long way to declare mapping. Okay, I get it now. Anyway, I told you I knew this was wrong, just didn't know how. Zombie to owner of zombie ID. And our last line, just to double check, storage, zombie, my zombies. Try again. Great, and we get this little animation. All right. Moving on to lesson 8. Are you excited? I am. All right. Let's finish writing the feed and multiply function. The formula for calculating a new zombie's DNA is simple. The average between the feeding zombie's DNA and the target's DNA. For example, function test DNA splicing. It's a public method. We have this number, we have that number, and we take the average. All right, sum them, divided by 2. Later, we can make our formula more complicated if we want to, but like adding some randomness to the new zombie's DNA. But for now, we'll keep it simple. We can always come back to it later. Put it to the test. First, we need to make sure that target DNA isn't longer than 16 digits. To do this, let's read this first and then go back to the code, and then I think that's it. All right. Because I keep getting ahead of myself, and they kind of like very walk through it. Anyway, first we need to make sure that target DNA isn't longer than 16 digits. To do this, we can set target DNA equal to target DNA modulus DNA modulus, and DNA modulus is defined up here. Kablamo. To only take the last 16 digits. Next, our function should declare an unsigned integer named new DNA and set it equal to the average of my zombie's DNA and target DNA, as in the example above. Note, you can access the properties of my zombie using myzombie.name and myzombie.dna. 3. Once we have the new DNA, let's call _create zombie. You can look at factory zombie.sol, we have been, tab, if you forget which parameters this function needs to call it. Note that it requires a name, so let's set our new zombie's name to no name for now. We can write a function to change zombies' names later. Note for you Solidity whizzes, not us. You may notice a problem with our code here. Don't worry, we'll fix it in the next chapter, winky face. Okay. So let's go back up and code this baby up. All right. So we're going to do target DNA equals underscore target DNA modulus DNA modulus. I think what's interesting is, so DNA modulus is defined up here, right? I think in some languages you need to do like super.DNA modulus. Whatever. Anyway, great. 2, our function should declare a unsigned integer named new DNA and set it equal to the average of my zombie's DNA. And all right. .DNA plus target DNA divided by 2, semicolon. Once we have the DNA, let's call create zombie. With not rand DNA, but new DNA. And they said we can put in any name we want here, but they want no name. Okay, let's check it. That went so much quicker and easier than our first, what do they call these? Chapters. All right, chapter 9. I'm going to get some water at chapter 10. Okay, more on function visibility. The code in our previous lesson has a mistake. If you try compiling it, the compiler will throw an error. The issue is we tried calling the create zombie function from within zombie feeding, but create zombie is a private function inside zombie factory. Hold on. Let's process this. We tried calling create zombie. Let's go back. From within zombie feeding. From within zombie feeding, which is where? Oh, wait. Yes. It's here. Create zombie is a private to zombie factory, but we're using it in zombie feeding. Okay. From within zombie feeding, but create zombie is a private function inside zombie factory. This means none of the contracts that inherit from zombie factory can access it. Wow. Internal and external. In addition to public and private, Solidity has 2 more types of visibility for functions, internal and external. Oh. Internal is the same as private, except that it's also accessible to contracts that inherit from this contract. Hey, that sounds like what we want here. External is similar to public, except that these functions can only be called outside the contract. They can't be called by other functions inside the contract. External is similar to public, except that these functions can only be called outside the contract. Ooh. They can't be called by other functions inside the contract. We'll talk about why you might want to use external versus public later. That's pretty interesting. For declaring internal or external functions, the syntax is the same as private and public. Contract sandwich, uint private, sandwich is eaten. Function eat is internal, and increments sandwich is eaten. Okay. BLT is a sandwich. Bacon sandwich is eaten. Eat with bacon returns a string. Public returns string memory. We can call this here because it's internal. Yes. Put it to the test. Change create zombies. Let's go. Where are we? Create zombie from private to internal. So our other contract can access it. We've already focused you back to the proper tab. Well, I clicked around a lot, all right? Anyway, check our answer. Blammo. All right, I'm going to be right back. I'm just going to get a cup of water. All right, I got my cup of water. Took a few sips. And let me just take a few sips here, rehydrate so I can talk more. All right. Chapter 10. My proper distance from the mic. All right. Chapter 10. It's time to feed our zombies. And what do zombies like to eat most? Well, it just so happens that crypto zombies love to eat CryptoKitties. Ah, yes, I'm serious. Ah, ha, ha, ha. In order to do this, we'll need to read the kitty DNA from the CryptoKitties smart contract. We can do that because CryptoKitties data is stored openly on the blockchain. Isn't the blockchain cool? Interesting. Don't worry, our game isn't actually going to hurt anyone's CryptoKitty. We're only reading the CryptoKitties data. We're not able to actually delete it. Okay, interfaces, cool. All right, for our contract to talk to another contract on the blockchain that we don't own, we first need to define an interface. Let's look at a simple example. Say there was a contract on the blockchain that looked like this. Lucky number. We create a dictionary, address keys, uint numbers, and we're calling it numbers. Function, set num, given an unsigned integer underscore num. It's a public function. Sender numbers num. Numbers is our dict. So we're putting a number. We're setting this person's number in the numbers dictionary. Okay. Get num. Get an address. Public view returns unsigned integer, and we're just looking up. We get an address, and we're looking up the number. Right? Get num. Set num. This would be a simple contract where anyone could store their lucky number, and it will be associated with their Ethereum address. Then anyone else could look up that person's lucky number using their address. Oh. Now let's say we had an external contract that we wanted to read data in. This contract using the getNum. Now let's say we had an external contract that we wanted to read the data in this contract using the getNum function. First, we'd have to define an interface of the lucky number contract. Contract number interface function getNum given an address. Public view returns uint. Oh, it's its own contract. Okay. Well, okay, I'm getting ahead of myself. I should read. All right. Interface of the lucky number contract. Notice that this looks like defining a contract with a few differences. For one, we're only declaring the functions that we want to interact with. In this case, getNum. And we don't mention any of the other functions or state variables. Secondly, we're not defining the function bodies. Instead of curly braces, we're simply ending the function declaration with a semicolon. So it kind of looks like a contract skeleton. This is how the compiler knows it's an interface. By including this interface in our dapps code, our contract knows what the other contract's functions look like, how to call them, and what sort of response to expect. Okay. We'll actually get into calling the other contract's functions in the next lesson, but for now, let's declare our interface for the CryptoKitties contract. Put it to the test. This is a long one. All right. We've looked up the Cryptokitty's source code for you and found a function called getKitty that returns all the kitty's data, including its genes, which is what our zombie game needs to form a new zombie. The function looks like this. You get a kitty, you give it an ID, it's an external view returns, and it returns all these. Wow. Kitty, storage, kit ID. Let's see. Oh, okay, cool. Let's read this. If this variable is 0, then it's not gestating. If is gestating, what is this? SI, is this here? Yeah. Is ready. Kit.cooldown gets is less than block number. Cooldown index next into action act. You cast it. Cooldown index. But you said, all right. So get kitty. The function looks like this. Okay, so you can just change what variables get output, and then they're just there. Okay, let's... Oh, that's what they're talking about. Okay, the function looks a bit different than we're used to. You can see it returns a bunch of different values. If you're coming from a programming language like JavaScript, this is different. In Solidity, you can return more than one value from a function. Yes. Now that we know what this function looks like, we can use it to create an interface. Define an interface called Kitty Interface. Remember, this looks just like creating a new contract. We use the contract keyword. Inside the interface, define the function getKitty, which should be a copy-paste of the function above, but with a semicolon after the returns statement instead of everything inside the curly braces. Okay. So I guess we put this in the interface of lucky number. What? What I'm wondering is just like, it's not clear if this contract goes inside this contract or not. I guess we'll find out soon enough. Anyway. Define a contract called Kitty Interface. It knew. Okay, that's a good sign. Remember, this looks like creating a new contract. We use blah, blah, blah. Inside the interface, define a get kitty, which would be a copy paste of the function above, but with a semicolon after the return statement. One too many, and that's for that, right? Okay. All right, let's put this contract outside of this contract. Or is it like included? So like this. No, like this. Oh, that's why. Create kitty interface here. Okay. I didn't change the UINT to 56 underscore ID. Try again, try again. What's going on here? Oh, got a bad copy and paste going on? Oh, I don't need it. What is it mad about? One. They want it here. They want it lined up. This is what I mean, like their error checker is really bad. Let's take a look at what they're doing. There are 2 parentheses to be closed. Really? Why? Returns. Right. And they're saying one more. Where? How does that make any sense? Where's the opening? Function. Get kitty. All right. Again, what the hell is going on here? Did I mess something up? That's good. All right, functions don't need the semicolons, just the lines. This is like terrible. Okay. Okay. Take out those lines. Is that what you want? Let's see what they say. Okay, that's better. Take out this line. Okay, so kind of like what I had before. Blank lines. All right. Anyway, let's take a sip of water and do lesson 11. Continuing our previous example with number interface. Once we've defined the interface as a contract, function get num, my address, blah, 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 we can use it in a contract as follows. Contract my contract, address type, number interface address, the address of the favorite number contract on Ethereum. Okay. Number interface, number contract, number interface address. Now number contract is pointing to the other contract. Function, some function. We can call getNum from that contract. So uint num number contract.getNum message of sender and do something with that number here. In this way, your contract can interact with any other contract on the Ethereum blockchain, as long as they expose those functions as public or external. Put it to the test. Let's set up our contract to read from the Cryptokitty smart contract. I saved the address of the Cryptokitty's contract in the code for you under a variable named CK address. In the next line, create a Kitty interface named Kitty contract and initialize it with CK address, just like we did with the number contract above. Okay, let's check it out. Initialize Kitty contract here using CK address from above. That's the contract number. Okay. Kitty, nope. So we have our address, then we want to make a Kitty interface named Kitty contract. and initialize it with equals number interface address. What? Name of the contract. Okay. Kitty interface, number interface. Oh, okay. Oh, okay. Kitty interface of CK address. Okay. That makes sense. We're making a contract using the constructor. Okay. Check our answer. Thank God. That took so much less time. Okay, chapter 12. Another sip of water. This getKitty function is the first example we've seen that returns multiple values. Let's look at how to handle them. It returns 3 numbers, A, B, and C, and you're returning 1, 2, and 3. Multiple returns. Process multiple returns, external A, B, C. This is how you do multiple assignments, so multiple returns, kind of like a dict in Python. Or if we only cared about one of the values, we can just leave the other fields blank. Cool. Put it to the test. Time to interact with the Cryptokitty's contract. Let's make a function that gets the kitty genes from the contract. Make a function called feedOnKitty. It will take 2 uint parameters, zombie ID and kitty ID, okay? And should be a public function. All right. Blah, 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 blah. Let's make a function. Define function here. Okay, we're going to make a function called feedOnKitty. And, oh. I didn't even notice I got some spam in my chat. I'll figure out how to block them later. Whatever. Where were we? It's gonna take 2 inputs, uint, zombie ID, and uint kitty ID, and it will be a public function. And it should be a public function. I think that's all there is to it. Yep. The function should first declare an unsigned integer named kitty DNA. Note, our kitty interface genes is a uint256, but if you remember back to lesson 1, uint is an alias for uint256. They're the same thing. The function should call the kittyContract.getKitty function with kitty ID and store the genes. Yeah. Okay. Oop. Store the genes in kitty DNA. Well, we need to do this, and they're saying, look up at the contract, and we need genes, so 10, right? So we need 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 commas. All we care about is the last one. Count your commas carefully. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9th. I need the 10th number. And we're going to put them in kitty DNA. Finally, the function should call feed and multiply and pass it both the zombie ID and the kitty DNA. And we shall remember to put our semicolons. And let's check our answer. Oh, bogus. What happened? Well, that is not how to do that. There we go. On to lesson 13. I'm so determined to finish this. 13, 14, 15. There's only 3 left. And yeah. We can do this. Our function chapter 13, bonus. Bonus? Kitty, it's not bonus, we're doing it. Bonus kitty genes. Our function logic is now complete, but let's add in one bonus feature. Let's make it so zombies made from kitties have some unique feature that show they're cat zombies. To do this, we can add some special kitty code in the zombie's DNA. If you recall from lesson 1, we're currently only using the first 12 digits of our 16-digit DNA to determine the zombie's appearance. So let's use the last 2 unused digits to handle special characteristics. Our function, all right, let's read that and actually understand it. To do this, we can add some special, okay, we're only using the first 12 digits and we're using a 16-digit number, right? Where does it say 12? Do we specify 12 anywhere? Anyway, we'll say that cat zombies have 99 as their last 2 digits of DNA since cats have 9 lives. So in our code, we'll say if a zombie comes from a cat, then set the last 2 digits of DNA to 99. If statements. If statements in Solidity look just like JavaScript. If blah, 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 in parentheses, curly braces, function call. Put it to the test. Let's implement cat genes in our zombie code. Let's first change the function definition for feed and multiply so that it takes a third argument, a string, which will store in memory, the name species. Next, after we calculate the new zombie's DNA, let's add an if statement comparing to the thing hash of species and the string kitty. We can't directly pass strings to the KECCAK256. Instead, we'll pass ABI.EncodePacked species as an argument on the left side and ABI.EncodePacked kitty as an argument on the right side. Okay. And modify, all right, add an if, now we'll add an if statement. If and this exactly. Right? That's what they're saying, but they want us to do species. And over here, they want kitty on the right side. Inside of the if statement, oh yeah, this is an if statement. We want to replace the last 2 digits of DNA with 99. One way to do this is using the logic. Okay, stay with me here. New DNA equals new DNA minus new DNA modulus 100 plus 99 semicolon. Assume it's 33455, then modulus is going to give you 55. Modulus of 100 is going to give you the remainder, 55. So new DNA, modulus minus, it zeroes it out. Finally, we added 99. You got it? Lastly, we need to change the function inside feed on kitty. Okay. When it calls feed and multiply to add the parameter kitty. Hard-coded. To the end. Check answer. Yes! All right, next chapter. Chapter 14. Ooh. Wrapping it up. That's it. You've completed lesson 2. You can check out the demo to the right to see it in action. Go ahead. I know you can't wait until the bottom of this page. Click kitty to attack and see the new kitty zombie get you. Well, you know what? I will do that immediately. So I click that kitty. New cat zombie generated. Oh, it has a tail. Try another combination. This kitty, it has a tail. This kitty with Santa Claus, it has a tail. Okay. JavaScript implementation. Once we're ready to deploy this contract on Ethereum, we'll just compile and deploy zombie feeding, since this contract is our final contract that inherits from Zombie Factory and has access to all the public methods in both contracts. Let's look at an example of interacting with our deployed contract using JavaScript and Web3. We have our API, we have our contract, we have our contract address, and we make a zombie feeding variable. Object. Assuming we're having our zombies in kitty's ID. To get the Cryptokitty image, we need to query their web API. This information isn't stored on the blockchain, just their web server. If everything was stored on a blockchain, then we wouldn't have to worry about the server going down, them changing their API, or the company blocking us from loading their assets if they don't like a zombie. Anyway, there's the API plus kitty ID. We're doing a $get operation. And we're doing the URL, do something to display the image, right? When these are clicks on a kitty, so we're using $kitty image, click on the function, zombie feeding, feed on kitty, pass it the 2 IDs. Listen for a new zombie event from our contract so we can display it. Zombie Factory, if error, blah, generate zombie. Zombie ID, result name, result DNA. Cool. Lesson 15. Oh, that's it. Let's see. Anyway, congratulations. You have completed lesson 2 of Crypto Zombies. Achievements unlocked. I've been upgraded to level 2. You've added No Name, a cat zombie, to your army. Awesome. Don't worry. You'll learn how to change her name in lesson 3. Show off your Cryptokitty Slayer to your friends. Share this URL. Blah, 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 blah. Okay. I'm going to proceed to the next lesson so that it at least saves it. Yeah. Advanced Solidity. I'm getting a little tired. We'll start the lesson. And then I think I'm going to end the stream so that it saves. Anyway. We made the zombie factory. The zombies attacked their victims. Solidity concepts. Cool. I love advanced topics. All right, now that you got some experience coding Solidity under your belt, we're going to dive into some of the more technical aspects of Ethereum development. This lesson will be a bit less flashy. Sorry, no plot twists, but you'll learn some really important concepts that take you closer to building real D-apps. Things like contract ownership, gas costs, and code optimization and security. You've been warned. No kitties and rainbows in lesson 3, but a lot of densely packed Solidity knowledge. We strongly recommend that you complete lesson 2 before starting this one. Well, yeah, I have. Start. Okay. Chapter 1, immutability of contracts. Anyway, so that's it. Thank you for tuning into the stream, and I hope you enjoyed it. Stop stream.